Then, of course, we're doing a lot of work on verification and test benches. We're using UVM. Uh, that for us means that we have a DUT, design under test, that includes the VPU, the CHI that we are using. That is the AMBA CHI protocol, AMBA 5 CHI protocol. It includes the NOC and the L2 home node. We basically first do the first version of this environment. UVM lets us to have reusable verification modules. So and to do constrained random simulations. We've been able to test all these different modes of operations of the accelerator thanks to this UVM environment. We will be looking into extending it. One thing that is, of course, it uses the coprocessor interface that we are developing with Cortus to talk to the core, and there is support for Spike, which is kind of the official RISC-V simulator, instruction set simulator. So we're by using Spike, we are able to actually co-simulate. We run the same code on Spike and on the hardware, and step by step, we are able to check the outcomes of each instruction and to verify the circuitry. So the Spike communicates with UVM through DPI, and we are, when instructions are completed, as I said, we are comparing them. We also have we are working on a test suite. We have the typical ISA, RISC-V ISA tests. We're using two random test generators. One's called RISC-V from Google. The other one's called Force RISC-V from Open Hardware. We're also working on assertions on this interface, and of course, if you want to do some good testing, you need to set up your CI/CD pipelines. We're doing for each merge request, we are triggering a pipeline to make sure it doesn't break anything. We have our regressions, also weekend tests that we can actually run longer tests, or we'll get to full benchmarks as well. But yeah, CI is an integral part of all of this as well. Okay, so that was the accelerator. Let's talk about the L2 cache home nodes a little bit. This stems out of the API project. It's a shared L2 cache from Forth and coherence home node from Chalmers. It's EMBA 5 CHI compliant. It has distributed slices with Messi protocol and configurable cache sizes, and programmable interleaving modes, NWAS set associative, and of course, well, it's inclusive of L1s, and it is the point of serialization. An L2 cache miss basically goes to the NOC and then goes to the memory. It can support lots of outstanding misses and coherence transactions, also cache management operations, CMOs, and cache allocation hints by the cores. It can also be configured as a scratchpad in runtime. At runtime, this can be done at page granularity. Portions can be configured this way. This scratchpad space memory is memory mapped on the DRAM physical address space. It's a load store interface. It doesn't require ISA extensions. It's work in progress to provide OS support and allocator for bookkeeping, configuration interface, and it can be cached in the level 1 data and level 1 instruction caches, and also kept coherent between the cores. There's also work on dead block management by Chalmers. The level 2 cache home node includes this mechanism to facilitate the eviction of cache blocks that have been deemed, let's say, dead by the software routine. Runtime identifies these dead inactive address regions based upon task dependency analysis. The runtime executes some custom demote instruction to issue some hints about these dead cache blocks. The core uses the modified CMO request to communicate that information to the shared L2 cache, and the L2 cache marks these individual cache blocks as to be evicted. Then we have the network on chip, the NOC. Here's an overall diagram of the how the NOC is connected. On one side, we have the core, another one accelerator, which has direct access. We have the L2 cache home node on another side. We have two I/O hubs. One's the high-speed one, one's the low-speed one. There's the I/O MMU that I will get to that can translate addresses in the high-speed hub. And we are also using a coherent link to go to an off-chip accelerator, which will be kept coherent with all the system. The coherent link can also be used to attach to another eProcessor in a dual socket configuration, and everything will be kept coherent. One thing that's missing here is the memory. We'll be implementing a DDR4, and that's for the second tape out, but that will also be on chip. So we have the NOC, the IOMMU, as I said, the coherent link. In the first tape out, we're using an FPGA to go to memory through this coherent link. The memory accesses will not be too fast, but it will enable us to test our abilities on how successful we can be doing a real tape out. And then over that, as I said, we will move this memory on chip for the second tape out. That will be designed by Cortus. The NOC features a 2D mesh, packet switching, credit-based flow control, multiple physical and multiple virtual channels. It's again EMBA5 CHI compatible. It features low latency channels that can bypass router pipeline stages and can do look-ahead route computation, and it can combine virtual channel and switch allocation. There's it's called a fast track path. It can do switch traversal bypassing, and then the minimum latency per hop from a virtual channel by doing this bypass can be the link traversal plus the delay introduced by this MUX. There's an HPCA paper that was on this very recently presented. The IOMMU that is being done by Forth at Vasis's group, who also helped to kickstart the RISC-V IOMMU task group for the RISC-V Foundation, and is acting chair. What it does is it provides virtualization for I/O peripherals. It can work with multiple concurrent contexts, TLBs, and caching structures. It can do hardware page table walks like a regular TLB and a regular MMU. It can work with multiple cache sizes, such as huge pages, and it can also work in non-blocking operation and hit under miss scenarios. There's also work going on in providing Linux kernel support for the IOMMU, and that is that. The coherent of Chiplink is provided by Extol, one of our partners. It's based on 25 gigabits per second serial lanes, up to 8 lanes, so that means 200 gigabits per second per direction. It works with also the CHI protocol, of course, which can work in between two eProcessor chips or eProcessor and an accelerator on FPGA, or as we will have the memory on FPGA for the first tape out, it can also do that. Basically, it wraps up the CHI packets into link packets for transmission. It's configurable. There's CRC for error detection, credit-based flow control, and yeah. So I think this is an overview of the IPs. I'm going to quickly also go over the slides for work package 6. This is the simulation and emulation work package led by Forth. This includes doing tests on architectural simulations, running our use case benchmarks there, and also micro benchmarks. This is to have a simulation infrastructure and a golden model, and to make some decisions on how the design should look like. And then there are all the FPGA tasks. One is a kind of like a shell, FPGA shell that we can use to connect with a host and to contain all of our IPs, and that can work as a software development vehicle for the single core system using the IPs that I presented earlier. And then there's the multi-core system version of that, of the FPGA emulator slash software development vehicle. In terms of Gem 5, these are using benchmarks from Work Package 3. Some are from NAS, some bioinformatics. These will be presented later. Of course, we can do parameter tuning of the out-of-order RISC-V model, play with the latencies, functional units, caches. We're currently in system call emulation mode. We will do full system emulation later of the single and dual core, running parsec benchmarks as well. And also RISC-V vector support on Gem 5 have also been introduced. And so we can get all kinds of interesting numbers to give us a good idea on how our architecture should look like. Coming to the FPGAs, we have selected 2 boards for evaluating our design. One's the VCU128, the other one's the Alveo 280 or U55C. They are similar FPGAs, and this task also provides FPGA shells to be used that have support for connection with the host through PCIe or DDR4, HBM, Ethernet, and also the chip-to-chip coherent link will be tested by the use of 2 FPGAs. Of course, we need the scripts and tools for all this. The area overhead is not too large, so we can, it fits in less than around, excuse me, around 5%. Sorry. So it fits in around 5% of the FPGA, giving us a lot of space to place our IPs and to have some kind of configuration with the whole set of our IPs that we can test on the FPGA. And once we pass that, then we are in obviously much better shape to go. It gives us good confidence to go towards the ASIC implementation. But of course, this is very important to get first. Currently work in progress. The core is being ported here, as I mentioned before. Working on generating FPGA images of the emulated chip that can boot Linux. That will be the SDV1 with the single core. And then there will also be the multi-core version of this SDV. Here are all the various IPs from the different partners. It's a bit outdated. These aren't TBD. These are provided by Cortus, these PLIC, UART. There's also a Clint. So we have a coherent link that can go to the next chip over in such a way that we can connect two FPGAs and have that working and have that tested on such a way. And we can also replace the second FPGA with the CNN accelerator from Thales that we will be using with the Thales application use case to demonstrate that we can actually add off-chip components to our eProcessor, and they will be coherent. work package 6 slides too.